Okay, so today we're going to discuss another topic. It's called Bromwich integral. So this is just a continuation of our discussion on residue theorem. So Bromwich integral is also known as inverse Laplace transform. Okay, so Laplace transform, we did this in previous course in 121, wherein we are given a function and we convert it using Laplace transform. Now, inverse Laplace transform is just the opposite of that. Okay. Now, we will see that this is actually an application of residue theorem. Okay. Now, to discuss this, we're gonna need to recall the definition of Laplace transform. So, for Laplace transform, we use capital L. So it's an operator, and it acts on the function f, and it's just equal to the integral from 0 to infinity of f of t times e raised to negative pt dt, which is just equal to some function capital F, now in a function of p. Now, notice that your f here, the small f, is a function of t, usually time, but it doesn't matter. Uh, in some cases, it's just time, and then it is being converted into another function capital F here, which is now a function of p, or another variable. Okay. Now, another thing that we need to recall is Fourier transform. Okay. There will be another discussion about Fourier transform in the last part of this course, but for now, we're going to need its definition. So Fourier transform is just f of x is equal to the integral from negative infinity to infinity of some function g as a function of alpha e raised to I alpha x d alpha. As you can see, this is very similar to the Laplace transform, wherein you have a function here being multiplied by some exponential function, right? Now, you can, in Fourier transform, you can conversely convert it vice versa. For example, you want to get g of alpha, it's equal to 1 over 2 pi integral from negative infinity to infinity of f of x e raised to negative I alpha x dx. Okay? So basically, this is your inverse Laplace Fourier transform. So this is your Fourier transform, and this is your inverse Laplace transform. Okay? Now, therefore, we do need to get the inverse version of this, which which we can obtain by following the same logic in this Fourier transform. Okay? All right. Okay? Now we can compare the first integral, f of x, right? It can be compared to the first for the Laplace transform, and then using this we can get f of t, right? And that would mean that is our inverse Laplace transform, right? Now, of course, we need to work this using residue theorem. Um, we can define, say, for example, uh, we want to get let's define first the Laplace transform of f of t, okay, first we let a variable p, so we need the p to get that. And let's say complex number, okay, meaning we can define it as p is equal to x plus iy, okay? And therefore, our goal, the f of p, to transform that, f of p, or capital F of p, can be written as capital F of x plus iy, okay? Or we can just define it as z also, which is just another variable for complex number. So this is going to be f of x plus iy. And then that is equivalent to the integral above, which is from 0 to infinity of f of t e raised to negative p t dt. Okay? Now, since we let p to be equal to x plus iy, we can, oh, sorry. We can change p here as x plus iy. That would mean our integral will now become the integral from 0 to infinity of f of t e raised to negative times x plus iy t dt. Okay? Now, using the law of exponents, we can separate the e raised to negative x times e raised to negative iy t, or rather e raised to negative xt, because we have to multiply t for both of these. So we're going to have two extra terms, and it's going to be 0 raised to, oh sorry, integral from 0 to infinity of f of t e raised to negative xt times e raised to negative iyt dt. Okay? Now, of course, this can also be written as, you can interchange the position of your integrand because they are just multiplying each other. We can write it as e raised to xt f of t e raised to negative I yt dt. And of course, we need to define some quantity here that our x is the real component of your p, which is greater some number k. Okay, so this is like a real number. Some real number. Okay, it could be 0, that's fine. Okay, now, now if you look at the table of Laplace transform, there is actually a equivalent function for this one. Okay, so you can check it in our reference. If you recall, we have a table there where in the function is given and the Laplace transform is also listed there. Even the inverse Laplace is also given there. So basically, this is a form of what we call this one. This is a form of PHYS transform. Because if you look at PHYS transform, you just have a function being multiplied. So here we have, let's say, g of alpha being multiplied by some exponential, right? So basically, this is just similar, right? So you have a function being multiplied by some exponential, right? Okay. Now, if we define this now or compare it with the table that we have, okay, you will notice that there is a function, okay, So from the table of Laplace transform, our e raised to negative iyt actually corresponds to this one because we have a negative I there, right? So negative I alpha t. So you can compare alpha to y and x to t, all right? So with that in mind, we can actually have some function phi of t, which is equal to e raised to negative xt f of t and 0. Now this is equal to e raised to negative xt ft if t is greater than 0, and it is 0 if t is less than 0. Okay, now of course, we will not care about the negative t here for now because our integral is just from 0 to infinity, right? So that means we can actually use this function in analogous with our Fourier transform, right? So if you look at here, we are trying to find f of t, and similar to Fourier transform, we just do it this way. So our f of t is our g of alpha, okay? So this means that our p of t can be written as 1 over 2 pi. Recall our here, our inverse Fourier transform. It's just 1 over 2 pi integral from negative infinity to infinity. Okay. Then we have our f of p. But our f of p is capital F of x plus iy e raised to iy t. And then we have dy. Okay. All right. Now using the definition that we have here, this is both, these two are both p of t. Let me fix this. Okay. We can change the value of our function. Okay. Now, how do we do that? So if we use this definition, okay, plugging it in to our, for example, the one that we want to find, which is just small f of t, this is just equal to e raised to xt times 1 over 2 pi integral from negative infinity to infinity capital F of x plus iy times e raised to iyt dy. Okay? So what happened here? We just added the this one, right? Because as we know, based on this definition, p of t is just e raised to negative xt f of t. Okay, to get f of t, we just divide p of t by e raised to negative xt, right? So this is just going to be p of t over e raised to negative xt, and this is just p of t times e raised to xt, which is why we have e raised to xt here. Okay? Now, now that we have this form, we can simply say, uh, simplify this. So we have e raised to xt here. And we do have another exponential here. Now, they both have the dependence on t, so we can actually combine these two. So we can write this as 1 over 2 pi integral from negative infinity to infinity of f of x plus iy. Now we have e raised to xt times e raised to iy t dy. Okay, now combining those two, we now have, so basically the same thing here, but now we have e raised to x plus iy quantity times t dy. Okay, now of course, if in our case we say t is greater than 0, okay, now in this case, if t is greater than 0, in this integration, our variable is y. So therefore, our x is just constant in this integration, right? So since x is some constant, let's say x is equal to some number c, then we can get dz, converted to dy dz. We have dz is equal to derivative of x plus iy. Since we assume x is constant in this case, then we only have I dy. Okay? And because of this, we can now rewrite this integral, right? So we assume x is constant. So our f of t, small f of t, our inverse Laplace transform, is just 1 over 2 pi integral from negative infinity to infinity of f. Now, in our case, we can uh, write x plus iy as z. So this is going to be f of z. Then e raised to zt, right? And then, of course, we can write this as, so we need dy. Okay, so from here, we have dy is equal to dz over I. Okay, so we're going to have dc over I. Okay, now we can transfer I because it's just a constant. So we're going to have 1 over 2 pi I integral from negative infinity to infinity of capital F of z e raised to zt dz. Okay, now does this look like a very familiar integration? If you look at this form, okay, so actually this is our, what do they call this one? This is our inverse Laplace transform, or our Bromwich integral. Oh, by the way, since we assume that we have c here as a constant, our integration will be different because our dc is now a complex number. So we're going to have we're going to need to make some adjustment in our bounds. So this is going to be some constant c plus I infinity, and then c minus c plus, or rather just c also, minus I infinity. Okay. All right. Now, looking at this form, we can actually think of it as this way. Integral from c minus I infinity, c plus I infinity of f of z e raised to zt dz is 2i, or 2 pi I, times f of t. right? Which is, if you look at our previous examples, what is something that is what is something that we multiply to 2 pi I in order to get our integral, right? So this is our integration problem, and the answer is just 2 pi I times f of t. Now, this is very common. Something that you multiply to 2 pi I to get the integral is actually your sum of residues. Okay? Now, of course, this is for t greater than 0. Okay? Now, therefore, since this is related to residue, our inverse Laplace transform f of t is just, okay? So, of course, we only need f of t, right? So, we don't need to multiply it by 2 pi I because our 1 over 2 pi I is here already included in our integration. So, basically, f of t is just the sum of residues of our function. Now, our function is the integrand. So, our integrand is f of c times e raised to zt. Now, here is a another common difference from what we're already been practicing. It should be all poles. Okay. Remember in previous examples, the residue that we are gonna use are only those inside your contour. But in this case, we are integrating in all complex plane. So we need all the residue from each poles. So you have to solve for the residue for all of the singular points. Okay? All right. So now that we know this formula, so this is the application, one of the application of our residue theorem. Okay? Now, let's use some example to illustrate how this actually work. Okay? So, example, find the inverse Laplace transform of capital F of P is equal to 5 over P plus 2 times P squared plus 1. Okay? Now, our goal is small f of t. That is what we want to find. Okay? So, the first step that we need to do, remember in our definition, we let p as they call this one, as complex number z, which is equal to x plus iy. So we're gonna do the same thing. Okay? The first step that we need to do is convert it to z. So now we have f of z. But another thing is we have to multiply it by e raised to zt because that is part of our integrand. Okay? So this is just going to be 5 times e raised to zt over z plus 2 times z squared plus 1. Okay? Now, what would be the next step? Of course, the next step is identifying our singular points. But the first equation does not give us all, right? Because if we look at the denominator, we have negative 2, but we still have here, we have z squared plus 1. Now notice that we can factor this into two binomial terms. So we have z plus 2. Factoring this, we're going to have z plus I times z minus I. Okay, don't be confused. We are now allowed to factor this because we are now dealing with complex numbers. Previously, you might say that this does not have any factor. Of course, if you are talking about real numbers, that you're right. But we are now dealing with complex number, so factorization this way is allowed. Now, what are our singular points? Okay, so we have poles, another term for singular points. So we have poles at z equals -2. We have poles at negative I, and we also have pole at positive I. Okay. Now, all of these are simple poles. So they are not they are not pole of order higher than 1, right? So we have simple poles here. So finding the residue should be simple, right? How do we get the residue again for simple poles? So for z equals -2, so the residue r at -2 is equal to the limit as z approaches -2 of z minus -2 times our function, which is 5e zt over z plus 2 times z plus 1 times z minus I. Sorry, z plus I. Now we can cancel out this, right? And then evaluate the limit. So we're going to have 5e raised to -2z. Remember, z we still have z there, so we're gonna substitute that. And then below, we're going to have -2 plus I times -2 minus I. Now, since you cancel out z plus 2, this can actually work better if you just use c squared plus 1, right? But that's fine because you know that this is still a sum and difference of two uh, terms. So we can write it as 5e raised to -2t. So we're going to have -2 squared plus 1, right? Which is just equal to 5e raised to -2t over, we're going to have 5. We have 4 plus 1. So finally, the residue at -2 is just e raised to -2t. So that is for the first one. Now for the second one, we're going to need the residue at I. So we have r at I is the limit of z minus I as z approaches I times 5e raised to zt over z plus 2 times z plus I times z minus I. Okay, so we can cancel out c minus I. Okay, and solving for that, we just substitute I to z. So we're gonna have 5 e raised to I t. Okay, and below we're going to have I plus 2 times I, oh sorry. Oh yeah, I plus I. Okay, so now we have 5 raised to, or 5 times e raised to it over 2I times I plus 2 or 2 plus I. Okay, that's fine. Either way, you can just write it as e or 5 e raised to it over 2 plus I times 2I. Okay, now solving for the final pole, negative I. We have r at negative I. It's just the limit as z approaches negative I of z minus negative I 5e raised to zt over z plus 2, z plus I, z minus I. So canceling out c plus I, we're gonna have 5e, so substitute negative I it over negative I plus 2 times negative I minus negative I, which is just 5e raised to negative it over, we can write it as 2 minus I, then times 2 or negative 2i. Okay, so that is our residue at negative I. 5e raised to negative it over 2 minus I times 2, or rather times negative 2i. Okay, so now that we have all the residue that we need, we can now finally get our inverse Laplace transform. Now remember, f of t or small f of t is just the sum of all the residues, right? So what do we have here? We have 3. The first one is e raised to negative 2t. The second one is 5 e raised to it over 2 plus I times 2i. And we have 5 e raised to negative it over 2 minus I times negative 2i. Okay? Now, you might think that this is enough. Yeah, this is correct actually. But of course, we need to have some function that makes sense. Remember, if you look at this equation, you still have your imaginary components. But in reality, your function is a real function. So we should uh, express this as a real function. Now, this solving this involves knowing the, what do you call this one? Knowing the definition of some functions that we already discussed. Now, as you can see, these two terms have some similar components, right? So we can simplify this. Okay, so hold on. All right, so you can use least common denominator, combine them. So you're gonna have e raised to negative 2t plus what would be our least common denominator. Of course, you can, this negative sign actually can be changed there. So you can have minus 5 e raised to negative it over 2 minus I times 2i. Okay, please do take note of that. But in this case, just 2 plus I times 2 minus I. Then we have 2i. Okay, now simplifying this, we're going to have 5 e raised to it times 2 minus I. Okay, and then we're going to have minus 5 e raised to negative it times 2 plus I. Now you can check this. If you separate these two terms into two fractions, does it go back to this original 2? If yes, then your expression is correct. Okay, now what do we need to do here? Now, looking at this expression, we can actually simplify this further, right? So if we consider this term only, okay, just to avoid rewriting everything all over again. So we're gonna have 5. So we multiply this 2 minus I. So we're going to have 10. We multiply 2 first. So 10, 10e raised to it minus 5i e raised to it. Then what else? And I have minus 10e raised to negative it minus, hold on. Okay, so we have negative 5 e raised to it times I, or e raised to negative it. So 5i e raised to negative it. In the denominator, we're going to have, we can multiply 2 plus I times 2 minus I, which is just 2 squared plus I squared. Or rather, minus I squared, right? Yeah. So we have 2 squared minus I squared. You can double check. It's going to be 4, 2i, then plus 2, negative 2i. You cancel the term. Then finally, you have negative I squared. Then 2 times I. Okay? So simplifying this term can be written as 4 plus, it's going to be just minus negative 1, because the I squared is negative 1, which is just equal to 5, right? So this means that this term can now be written as 10e raised to it minus 5i e raised to it minus 10 e raised to negative it minus 5i e raised to negative it over 5 times 2i. Okay? Now, as you can see, we can divide everything in the numerator by 5 because all of those are multiples of 5. So we can simplify this as 2 e raised to it minus I e raised to it minus 2 e raised to negative it minus I e raised to negative it. Everything is divided by 2i. Now, one thing that you might notice is in the numerator, you have everything as e times, or sorry, e raised to it, or either also e raised to negative it. Now, in this case, you can combine all the, what do you call this one? All the real, not really real, rather, all the terms with imaginary in as a coefficient, okay? So let's see, what do we have here? So we have the first, we have 2 e raised to it. Then we must subtract it with 2 e raised to negative it. So we just combine them because both of them have real coefficients. Okay, we don't have I there. The next, we're going to have minus IE raised to IT minus IE raised to negative IT. Everything is divided by 2i. Now, looking at this, we can separate the numerator. So we're going to have 2 e raised to it minus 2 e raised to negative it divided by 2i. And then we subtract. So since both of these have negatives, we can just factor out the negative. And this is going to be e raised to it plus e raised to negative it all over 2I. So we put I there. We factor out I, negative I. So as you can see, we can also simplify the first term. The 2's here, can cancel them. And this is going to be e raised to it minus e. Oh, no, that's not going to work. You can do that, but we do need the 2 in the denominator. As you might have noticed, this is very familiar. So if you have a difference of exponentials with alternating sign in your power, then you divide it by 2 or 2i, it's going to be either cosine or sine, right? So in this case, we can just factor out 2. Then this is going to be e raised to it minus e raised to negative it over 2i. And then we can cancel out I here. So we have minus e raised to it plus e raised to negative it over 2. Now this is sine t. And this one is cosine t. So therefore, the final answer for that is 2 sine t minus cosine t. Now finally, our f of t can now be written as e raised to negative 2t plus 2 sine t minus cosine t. So that is how we solve for the inverse Laplace transform. Now, if you go back to the table of Laplace transform, you will need to see these functions and figure out what is the equivalent Laplace transform for this one and for this one. Then you're going to add those three, and finally, you're going to get the original problem, this one. Okay, that's why it's called inverse Laplace. So the Laplace transform will give you this, but the inverse Laplace transform will give you f of t, which is what we got here, which is e raised to negative 2t plus 2 sine t minus cosine t. Okay, so that is our final answer.